The carbon dioxide or CO2 gas laser is one of the most established and versatile surgical lasers, recognized for its exceptional precision and control in soft tissue procedures. The CO2 laser operates as a molecular gas laser composed of a mixture of carbon dioxide, nitrogen, and helium. It emits infrared radiation at a wavelength of 10.6 micrometers, a frequency strongly absorbed by water and organic tissue. Within the laser system, electrical discharge first excites nitrogen molecules, which then transfer energy to CO2 molecules, causing vibrational transitions that release infrared light. This emitted light is then amplified and focused by optical resonator mirrors, creating a powerful, coherent beam. Depending on the clinical need, the CO2 laser can function in continuous or pulsed modes, allowing precise control for cutting, vaporizing, or coagulating tissue with minimal damage to surrounding areas. The internal design of the CO2 laser system integrates several critical components to maintain efficiency and beam stability. Inside the discharge tube, the gas mixture flows continuously between electrodes, where high voltage excitation sustains the lacing process. A water cooling ring and tubing system circulate coolant through the device, preventing overheating during prolonged use. The total reflective mirror at one end reflects the infrared light back and forth through the discharge tube, while the laser output mirror at the opposite end allows a controlled portion of the amplified light to exit as the laser beam. Gas return lines recycle the gas mixture, while precise water and gas inlets regulate flow and pressure, ensuring optimal beam quality and thermal stability during operation. To sustain continuous and uniform laser emission, the optical and thermal management systems work together. A tangential blower maintains consistent gas flow across the discharge region, while the heat exchanger removes excess heat from the gas stream. Fold mirrors direct the laser beam along a compact path to maintain alignment and minimize optical loss. At the same time, RF electrodes provide radio frequency excitation that energizes the CO2 molecules, generating consistent infrared output. A real-time power monitor measures the beam's intensity to ensure stability, while the output mirror and window release a focused laser beam for use in surgical or dermatological applications. This integrated architecture maximizes power efficiency, beam precision, and device longevity. Once generated, the laser beam is delivered through a carefully designed optical pathway that preserves its intensity and focus. The beam exits the CO2 laser head and passes through an adjustable coupler connected to a hermetic unit, which seals the internal components against contamination and controls cooling gas flow. The energy is then transmitted through a flexible PIR fiber optic cable to the handpiece, where a focusing lens concentrates the beam to a small, precise spot. The surgeon or operator positions the handpiece approximately 3 to 4 millimeters from the tissue surface, enabling fine control over incision depth and thermal spread. This configuration allows the CO2 laser to achieve extremely localized ablation, producing smooth, uniform tissue removal while minimizing collateral damage. Routine maintenance ensures consistent performance and patient safety. Key maintenance tasks include mirror alignment and beam calibration, verification of gas pressure and mixture integrity, and regular cleaning of the cooling system and optical filters. Preventive care involves protecting optical surfaces from dust and replacing O-rings and seals to prevent leaks. Output calibration is verified using an optical wattmeter to confirm laser intensity. All maintenance adheres to ANSI Z136 laser safety standards, ensuring the system operates safely and effectively across clinical environments. The CO2 laser's novelty lies in its combination of precision, safety, and adaptability. It remains the first surgical laser to achieve widespread, long-term clinical success and continues to enable bloodless, contact-free surgery with exceptional tissue control. Because it selectively targets water-rich tissue, it minimizes thermal damage and accelerates healing. Its capabilities serve as the foundation for modern fractional CO2 lasers in dermatology, now used extensively for skin resurfacing and scar reduction. The laser also integrates seamlessly with robotic surgical systems, expanding its utility in advanced microsurgical and minimally invasive applications. Finite element analysis of the CO2 laser's interaction with biological tissue demonstrates its precise thermal and spatial control. Nearly 90% of its energy is absorbed within 0.1 millimeters of tissue depth, confining the thermal effect to a microscopic zone. This localized energy deposition rapidly vaporizes intracellular water, achieving clean ablation with minimal collateral injury. The thermal damage zone remains under 100 micrometers, preserving adjacent healthy tissue. Peak tissue temperature reaches approximately 100 to 120 degrees Celsius at the incision point, while surrounding areas remain below 60 degrees, maintaining cellular integrity. Pulsed operation further limits cumulative heat buildup, and peripheral cooling enhances safety by reducing unwanted thermal diffusion. Clinical studies consistently show that CO2 laser treatment results in faster healing, reduced pain, and lower infection rates compared to conventional scalpel surgery. Blood loss is minimal due to the laser's ability to coagulate small vessels upon contact, while sterilization of the incision site dramatically lowers postoperative complications. Patients also experience shorter recovery times and improved cosmetic outcomes, as shown by smoother, rejuvenated tissue after treatment. These results confirm the CO2 laser's superiority in both functional and aesthetic outcomes, establishing it as a gold standard in precise, minimally invasive surgery. The CO2 gas laser continues to set the benchmark for precision, safety, and efficiency in modern surgical and dermatological applications.